Assalamualaikum warahmatullahi wabarakatuh, and welcome back to my video. So let us today continue with our class, still on the topic of transformer, and today we look in details the subtopic of the PU, or the per unit system of measurement. So in the single phase, here is the introduction. So you can see in the first paragraph that in the PU system, so the voltage, currents, powers, impedance, and other electrical quantities are not measured in their usual SI units. For example, volts, amperes, watts, ohms, etc. etc. However, this electrical quantity is measured as a decimal fraction of some base level, whereby the per unit basis by equation is shown here. So the quantity per unit is equal to actual value over base value of quantity. So now in this slide, it presents that in the single phase, these relationships are first the P base, and second the Q base, the reactive power, as well as the S base, okay, is equal to V base times I base. And then here the fourth quantity we have Z base. So how the relationship? So we have V base over I base. Meanwhile for Y base, okay, the quantity number 5 equal to I base over V base. And then Z base equal to V base square over S base. And then if you want to learn more about the PU system, or the per unit system, you may go to my channel, YouTube channel over here, and watch chapter number 8 here. So this is what I have recorded earlier in the subject of polyphase circuit. Okay, topic number 8A, for example, up to topic number 8B. So we have altogether 1, 2, 3, 4, 5, 6, and 7 videos discussing particularly on PU, or per unit system. So now back to our slide. We continue with example 3, where the question says a simple the simple power system is shown in figure 3. So how figure 3 looks like, okay, I will show later in a different PowerPoint. So this system contains a 480 volt generator connected to an ideal 1 to 10 step up transformer. Okay, so 1 to 10 step up transformer. So a transmission line, an ideal 20 to 1 step down transformer. So we do have actually two number of transformer. First, the step up. Okay, basically this is located at the generator side. Okay, and then in between we have a transmission line before end up at the step down transformer, the second transformer. Okay, as well as the load. So the impedance of the transmission line is 20 plus J60 ohms, and the impedance of the load is 10 to 30 degree ohms. Okay, the base values for this system are chosen to be 480 volt and 10 kVA. Okay, the parent power S at the generator. All right, so this is the base value again for the system. I mean for the voltage, as well as the base value of the system, the S, or the parent power. So first you need to find the base voltage, the current, the impedance, and the parent power at every point in the system. So secondly, you need to figure out or convert the system to its PU equivalent circuit, and then find the power supplied to the load in the system, so the P. Okay, so find the power loss in the transmission line, right? Okay, so the solution is shown in this particular slide. Okay, example number 2, example number 3. Okay, now we jump over to the figure. So this is the figure we have in this example. We have region number 1. So let me put a partition, the red line, in between region. So we have region number 1. This is the generation side. So we do have our voltage supply or the generator supply over here with the IG generator current. So before we move to the first transformer, which is the step up transformer with the ratio of 1 to 10, and we move on to the second region. So this is transformer number 1, for example, TX1. So and then we have this one in between. Region number 2 is the transmission line, TL, with the line impedance 20 plus J60, 60 ohm, okay, as well as the I line, of course. And then we come to the second transformer, TX2 over here, okay, located at the load, or connected to the load with 10 30 degree with 30 degree ohm, okay. And of course the I load, and also the ratio, return ratio of the transformer, the step down transformer, 22 to 1, okay. So this is the symbol of A and A. So A number 1 and A number 2. So this is how we can understand from the figure. So now in generator region, so V base equal to 480 volt, and then the parent power S base equal to 10 kVA. So this has been chosen or has been selected in the question. Okay. So I base equal to S base over V base 1. So this is in region number 1, where we have our transformer number 1. So I base again equal to S base over V base 1. So substitute this value S base into 10, which is 10,000 VA or 10 kVA, as well as the V base. Okay. And resulting I base, it is 20.83 ampere. And then the second quantity, so calculate Z base 1, which is equal to V base 1 over I base 1. So Z base 1 480, and I base 1 is the value we just calculated above here. And yielding Z base 1 equal to 23.04 ohms. And then the turn ratio of transformer T1 is A equal to 1 over 10, right? Or 0.1. Okay, so the base voltage in the transmission line is, or the transmission line region is V base 2 equal to V base 1 over A, or this is actually equal to V base 1 over V base 2. Okay. And of course, you need to rearrange the equation into here, and finally substitute the value of V base 1. Again, this is provided in question here, alright? And then this is not comma, but it's a dot over here. Okay, 0.1, okay, is the value of A. And then again, giving V base 2 equal to 4.8 kilovolt. Okay, so next, after we obtain value of V base 2, we are able to calculate the next quantity in region number 2, where we have our transmission line. So this is region number 1, region number 2 in between, and here is region number 3. Just to recall what we have seen in the figure 3. So this is number 2. We do have over here the transmission line. So we still have the same value of S base 2 okay, which is 10 kVA. All right. So what about the value of V base 2, the second voltage or the second base voltage? It is actually taken from previous V we just calculate in this example or in this part. Okay, 4,800 volt. Okay. So normally, okay, we can also rewrite the equation over here. We have S base 2 okay, over V 2. Okay. So 10 kVA for the S base all the way from beginning until the load part or the load section is unchanged or similar, we stick to 10 kVA. Okay, and substitute here and giving I base 2 equal to 2.083 ampere. And then what about Z base 2? Sorry, Z base 2, this is nothing but V base 2 over I base 2. Okay, so V base 2 here is the same value, and I base 2 is taken from the above calculation, right? And thus V base 2 equal to 2304 ohms. And now as we move on to the third region, now we have done with this region, so all the quantities involved, and we have come up with the base value. And now we try to jump over to part number 3 or region number 3, crossing A2, the second A, okay, whereby second A, the ratio is 20 to 1. It is a step down transformer actually. Okay, so A2 equal to 20 over 1. Okay, so the turn ratio of the transformer T2, right? So this is A for T2. So A equal to 20 over 1 equal to 20. So the base voltage in the load region is again, so we just repeat the similar steps what we have done in previously, but this time around we have V base 3 equal to V base 2 over A. We can actually rearrange, or it is actually originally come from VB2 or V base 2 over V base 3 or VB3, and then rearrange into here, and again take the value of V base 2, all right, so which is 4,800 volt over 20, okay, the turn ratio giving V base 3 equal to 240 volt. So now unchanged value of S base, stick to again 10 kVA, and I base 3 we have S base 3 over V base 3. Okay. Substitute value and giving I base 3 equal to 41.67 ampere. And Z base 3 here, this is a thing, this is about VB3 over IB3. So remember this one, IB3, we just obtain the value here. Okay. And resulting the value of Z base 3 equal to 6.76 ohms. So we have done with all the quantities, the base quantities for all regions. Now, to convert the power system to a PU system, each component must be divided by its base value in its region of the system. So the generator's PU voltage is its actual value divided by its base value. So this is the actual value of the generator, and we have the VG. In that case, we have VGPU equal to 480 degree, 440 with 0 degree volt over 440 volt. This is the base. So for the base, we have peak, and this is the actual in the system. And we do have VGPU 1.0 with degree of 0. okay, PU. Now the transmission's PU impedance is its actual value again divided by the base value. Okay, so we have actual over base, and we do have over here Z line PU. This is what is provided in this question as the so-called the actual value divided by the base value 2340, which is the ZB2. Alright, so where is the ZB2? Is over here. So let me color in different color. Let me pick a different color so we can clearly see the value. So this is the Z base 2. Alright, so base 2 means the second region. Remember just now, fall under transmission line. Okay, so Z line PU 2304 as the base value of the Z, and then giving Z line PU equal to 0.0087 plus J 0.00260 PU. Now moving on, so we have the load's PU impedance is also given by actual value divided by base value. We have a Z actual of the load, for example. So for the load divided by Z base 3, right? So we do have 0 stand with angle of 30 ohms divided by 6.76, and I believe this is taken from sorry, Z base 3. Let's double check. So yes, here Z base 3. Right? Remember what? Because the load is located in region number 3. Right? And then at the end of this analysis, we are able to come out with the equivalent circuit or the PU equivalent circuit shown in figure 3A above or below. So the PU circuit equivalent circuit for example 3. So this is the generator. So we have the IG, we have the IPU, we have connected all the quantities or all the elements in series, starting from the Z line PU, here the transmission line PU, as well as the Z load PU, whereby IGPU equal to I line PU equal to I load PU equal to IPU. Alright. Okay, now is the current flowing in this PU unit system is IPU equal to ZPU over Z total PU. So you just need to apply a KVL approach in order to solve this closed loop circuit. Alright, and by doing that, you're supposed to manage to get this or to obtain this equation. So IPU equal to ZPU over Z total PU. So we have ZPU, the generator voltage per unit, which is 0 degree, over this is Z line PU. Okay, just to recall. Okay, and then this is nothing but Z load PU, right? And then by solving this, the final IPU equivalent to 0.6569 negative 30.6 degree PU. Okay. Therefore, the per unit power of the load is, so since we have calculated the value of IPU, therefore we can actually calculate the load PU. Okay, is equal to I square PUR PU. So I square is this value, all right, into here and square it. So what about RPU? This is the value of resistance value. So for the load. Okay, so the load is given by this value. Okay, 1.736 the PU value and 30 degree. So what this is in polar form. So remember, once you convert to rectangular form, so it consists of real and imaginary part. Okay, the R plus G dx, okay, the resistance and also the reactance. Okay, so take the R value, R of the load. Okay, this is R for the load. Okay, which is 1.503 into here. Since you are calculating the power of the load. Okay, so giving P load PU equal to 0.487 PU. Right. And to add to that, the actual power supplied to the load is, so we have basically this equation where we have the S base equal to P load actual, all right, over P load. Okay, so we have a P load over here as base. Oh, sorry, not this one. So we have rearranged the equation into of P load actual or PU. Okay, this is equal to P load actual, all right, over S base. Okay, here. So this is the relationship of the P load PU. This is equal to P load actual over S base. Not SB, but BS. Oops. Yes, this is SB. Yes, correct. And then rearrange, we can get the actual P load. So P load PU multiplied by S base. S base, remember, stick to 10 kVA. And here you just calculate right above here. Okay, 0.487. So giving the P load actual equal to 4.87 kilowatt. And then the D, the PU power loss in the transmission line is P line PU equal to I square PU RPU. So this is equal to 0.569. Okay, the same value of I, but now we take the value of R from transmission line. All right, so transmission line, I believe this part is belong to transmission, the line or the Z line PU. So take the R value 0.087, right? 0.087 over here. And giving the line PU, the P line PU 0.00282. So similarly for the P line actual loss in the transmission line, so we have over here the P line, okay, EU, this is equal to P line actual divided by S base. Okay, so then you need to rearrange into here in terms of P line actual, then just substitute the value of P line, just calculate here and S base 10 kV, and giving the P line equal to 28.22 watt. Right. Now back to our slide. We will continue with voltage regulation, VR, and efficiency. Right. So we can see over here, as we can see over here, this is the full load regulation. That compare between the VS no load and VS full load. Okay, this is how we define the voltage regulation or the full load voltage regulation. So this is the symbol or the notation of the voltage regulation VR. So this is equal to VS. Again, this is the for the secondary. Okay, S stands for the secondary side of the transformer. Okay, and NL is no load. So minus Vs full load over Vs full load times 100%. Okay. However, at no load, Vs equal to Vp over A. Okay, so this is once we refer to secondary side of the transformer. Okay, so we can simply say that this condition or under this condition, that Vs equal to Vp over A. So just substitute over here into this equation back to the V equation. So now we have Vp over A minus Vs full load over Vs full load times 100%. Alright, so this is the equivalent circuit on how we can understand how the voltage regulation works. So this is actually referring again to the secondary part of the transformer. So we have Req as JXEQ, where Req consists of Rp over A squared plus Rs, and Jx or XEQS consists of Xp over A squared plus Xs. So we have Vp over A as the no load alright, over here voltage, and we have AIP. So the phasor diagram is used to determine voltage regulation. So this is the equation after we simplify, we obtain from this diagram. Again, we apply KVL. So Vp over A equal to Vs plus Reqis plus Jxeqis. So we are going to use many equation later on, okay, especially this type of equation. So full load voltage regulation is a quantity. Okay, this is a repeating slide. Sorry for the mistake. Okay, but it shows that the VR is actually equal to Vp over A minus Vs full load over Vs full load multiplied by 100%. It's just a repeating slide. And the efficiency, yes, here is the example of the voltage regulation once we represent in the phasor diagram. So we do have over here a lagging power factor. So how do we know? So basically we can refer to the quantity of or the element of Is, okay, the secondary current. So it lag behind Vs. So Vs always be our reference. Okay, so if you look at so this is of course during the full load, right? So this is a Vp over here, Vp over A, this is a Vs, so no load. Okay, so it happens over here that if you look at the size or the length of the line, the blue line over here, the thick blue line or the arrow, is much longer compared to the Vs. All right, this means we can say that the magnitude of Vp over A is greater than Vs. Okay, and due to that, okay, here Vp is bigger, greater than Vs, and from here let's say we have 5 minus 2, so it will give a positive result. So it will give a positive voltage regulation. Okay, and then the second condition is the unity power factor. Again, refer to the Is location or position. So it is actually in line with Vs, and we know that the phasor diagram is under relation of unity power factor. And if you look at the value or the magnitude of Vp over A and compare it with Vs, it is slightly longer or bigger. So we can write that Vp again in this particular example or in this particular condition is bigger than Vs, right? And then result in a positive voltage regulation. Somehow, if you refer to leading power factor of the phasor diagram, now Is is okay, leading Vs, or it is now located above the Vs and with shorter Vp over A, okay, compared to the Vs in terms of its magnitude. So now we have Vp over here, Vp over A, which is smaller than Vs. So smaller than Vs meaning since we have Vp over A minus Vs over Vs. So since this value is smaller than Vs, let's say we have 2 over 5. So always give negative answer or negative voltage regulation. All right, now how about the transformer efficiency? Okay, so the efficiency equal to P out over P in multiplied 100%. So P out stay as P out and P in is actually P out plus P loss, right? And then since P out occur equal to Vs Is cos theta s, okay, so because it occurs at it taking place at the secondary side of the transformer again, that's why we consider all the secondary value or secondary quantity of Vi as well as the power factor. So again, efficiency equal to Vsis cos theta s over Vsis cos theta s plus Pcu, the losses in terms of copper losses, and another type of losses which is the core losses. So how about the equations? So copper losses is nothing but I squared times Reqs, right? The secondary. And then in the other hand, P core, the core losses equal to Vs squared over Rc. Okay, so the core losses. Example number 4, a 15 kVA, the parent power, so 2300 230 volt. So this is obviously a step down transformer, is to be tested to determine its excitation branch components. So excitation branch component consists of RC and XSM. Its series impedance and its voltage regulation. So the series impedance is Req, right? So and also Xeq. So the voltage regulation, of course, the VR. So the following test data have been taken from the primary side of the transformer. So we do have basically two types of tests, namely open circuit test plus the short circuit test. And these tests taken at the primary side of the transformer. Right? So the VOC, IOC, POC. So again, the VSC, ISC, and PSC. So first, find the equivalent circuit of this transformer referred to high voltage side. So find the equivalent circuit of this transformer referred to the low voltage side. So we have the high voltage side. In this particular example, is referring to the primary side. Okay, high voltage side means 2300 volt, or happening at primary side. So about the low voltage side? So the low voltage side is taking place at 230 volt or secondary. Okay. So calculate the full load voltage regulation. So meaning we need to calculate the full load VR at 0.8 power factor lagging, unity power factor 1.0, and 0.8 leading power factor. So what's the efficiency of the transformer at full load? So we need to find the efficiency at full load with a power factor of 0.8 lagging. So you need to pick all the data from 0.8 lagging power factor. So data must be taken from this analysis. Okay, now we go to the solution, okay, of example 4. All right. So the excitation branch value of the transformer equivalent can be calculated from the open test data. So this means for open circuit, so we might be able to get the value of excitation branch impedance that consists of RC plus X SM, the magnetizing reactance. Okay. And series element can be calculated from short circuit test. Meanwhile, for short circuit test, we managed to get R EQ, all right, plus X EQ. And then from the open circuit test data, the open circuit impedance angle is here. This is what we have seen in this slide. Previously, we have arc cos theta times POC, the power of first circuit over VOC, IOC. So just substitute the value of the P, V, and I from the question and giving us the theta open circuit theta, which is 84 degree. And thus, the excitation admittance Y E equal to IOC VOC. Again, this is what we have came across in the slide earlier. So substitute the value of theta. So remember the negative angle over here. All right. So IOC VOC again, you just pick from question. Okay, just pick from question and substitute into this excitation admittance, and then giving YE equal to 0.000095 minus 0.000908 ohm. Okay, so the element of the excitation branch referred to the primary RC and SM, okay, giving 10 k ohms plus 11 k ohms. So we have done with the RC and SM. So now we use the short circuit data in order to come up with this series impedance. So theta SC cos arc cos again theta PSC over VSC ISC. So substitute again all the value 160 for P, 47 volt, 6 ampere, giving the theta, the short circuit theta equal to 55.4 degree. So the equivalent series impedance thus ZSE equal to again ISC over ZSC. This is the equation. Again, we have seen earlier, and then giving us the value of series impedance is 4.445 plus G 6.45 ohm. Right. And thus from here we just directly pick or choose this value as REQ and this value as XEQ. Right. So we have done with the first equation, or with the first question, so which is referred to the high voltage, and now to find the equivalent circuit referred to the low voltage side, it is simply necessary to divide the impedance by A squared. Okay, since A equal to NP over NS equal to 10 and the resulting values are, so we can see from the question A is actually 2300 volt over 230 volt. So this is equal to 10. Okay. But we have to divide by impedance by A squared. So you need to square the value A. This means the value A squared equal to 100. Giving RC equal to 1.05 k ohms, SM equal to 110 ohms, REQ equal to 0.000445 ohms, and SEQ equal to 0.0645 ohms. And see, the full load current on the secondary side of the transformer is IS rated equal to S rated over VS rated. So this is again from question 15 kVA. So VS rated, so this is on the secondary side of the transformer, the ratio, the voltage ratio here, 230 volt, and I believe this is provided in the question. And then finally giving the IS rated equal to 65.2 ampere. And from there to calculate Vp over A, use equation below. So this is again derived from the KCL of the equivalent circuit of the transformer. Okay. Vp over A equal to Vs plus Req Is plus Jseq Is. Okay. And then this all actually we have been calculated. All this have been calculated have been provided. Okay. So we just need to substitute and solve the equation. But before that, remember the condition given in the question. So the first condition is power factor 0.8 lagging. That means the current Is here is the rated current, the S rated current, the Is. So we have negative angle of 0.8, up cos 0.8. So we have data over here. Let me write it for you. So we have up cos 31 0.8. Okay. Since it is a lagging condition, so make sure put sign of negative sign. Okay. So now 36.9 degree. Okay. Therefore Vp over A, so 230 volt 0 angle is actually dV, the value of Vs. Okay. Plus 0.0045, this is Req, right? This is Req, right, at the secondary here. Okay. After the circuit, the whole circuit or the whole equivalent circuit referred to the secondary or the low voltage side. Okay. So this is actually Is, all right, Is, and then plus J, so this is Xeq, again referred to the secondary side of the transformer is from here. Oops, from here. And as well as the, again, Is. So solve the equation carefully and then giving us the value of Vp over A equal to 234.85 0.4 degree volt. So resulting the voltage regulation is Vp over A minus Vs full load over Vs full load. So Vs full load is the is provided again in the question. So we have just calculated the value of Vp over A, thus giving Vr equal to 2.1%. So you may double check the answer, which is always positive due to the lagging condition. So we have seen this positive value in the previous slide under the phasor diagram side topic. So what about if you have a unity power factor? So unity power factor, so of course we have 0 over here. Okay, so just up cos 1.0 giving us the angle 0. Okay, so though this is not minus, don't get confused, this is equal. All right, this is actually equal, this is also actually equal, not negative. Okay, this is equal, this is equal. Is equal to, I don't know what happened to the symbol, so one line is missing. This is actually again equal, and this is equal, not negative. All right, so S equal to 65.2 0 angle degree. So therefore again, so use the same equation, but this time around we have a different value of Is here, this Is, okay, because it is also associated with the power factor, okay, especially the angle, right? So from here we can solve the equation that giving us the value of Vp over A. So 232.94, 1.04 volt. Okay, then put into VR equation, so still got the positive value of VR, 1.28 degree. Now the power factor 0, if power factor equal to, again it's not negative but equal to 0.8 leading, right? So current IS equal to 65.2, so this is the value. Again, the arc cost of 0.8, so positive value due to the leading condition. So therefore, again, this is wrong. This is yes. This is not negative but positive. So this is the value of IS. So this is the value of IS. Okay, with positive value. So with the positive value of angle. So giving with the VP over A equal to 229.85, 1.27 volt. And this is smaller than the VS full load, that give us the negative value of VR. So negative value, right? So now D, to find the efficiency of the transformer, first calculate its losses. The copper losses are, so this is taken from the previous equation. So P copper equal to IS square REQ, 65.2 is the value of the IS, and square it. So the REQ is 0.00445 and giving us the PCU equal to 189 watt. Okay, so meanwhile, for the core losses are given by, again, the equation. This is taken from previous slide. We have VP over A squared over RC. So remember to take the value of RC, which is 1050 ohm. So VP over A here is actually from the 0.8 lagging. All right, 0.8 lagging is over here, and this is the value of VP over A here. Let me change the color. Okay, VP over A. So why we take the value of 234 as well as the REQ over here, blah blah blah, because the question asks you to calculate the losses or the efficiency of the transformer under 0.8 power factor leading. Okay, so just pick value of 234.85 watt. Okay, giving P core equal to 52.5 watt. And thus the output power of the transformer at this transformer of this power factor is P out equal to VSIS cos theta. So VS 230 volts, so IS 65.2 ampere, and cos 36.9 degree. So giving the P out equal to 12 kilowatt. So therefore, the efficiency of the transformer at this condition is, we have P out over here, which is a VSIS cos theta. Here again, VS is P out, okay, plus the copper losses, the core losses, and substitute the value 189, 52.5 watt, as well as the P out 12 kilowatt, and giving so the efficiency equal to 98.03%. Alright, thank you very much for watching. I hope we can continue in the next video for the three-phase transformer. Have a nice day. Signing off.